Okay, so welcome to this video on HL bonding. This is going to be a fairly short one, and it's actually going to be all of HL bonding. There's only two sections to it, and they're both fairly compact. So let's get into it. So we're going to start with 14.1, which makes sense, which is looking more at how bonds are formed and the different types of covalent bonds we see. So covalent bonds, we're going to talk about how they form in terms of atomic orbitals. We're going to talk about formal charge and then how that links to exceptions to the octet rule, which we looked at earlier. We're also going to look at delocalization and resonance. Okay, so before we get into the specific types of bonds, I'd like to talk about covalent bonding in general. So we talked about covalent bonding as being that sharing of electrons. But let's zoom in slightly, as we tend to do in HL, and have a look at what we believe is happening on a slightly more detailed level. So covalent bonding is where I have an orbital on one electron that is partially occupied and an orbital on another atom that is also partially filled. What then happens, and it's not helpful that I did those in the same colour, is it? What then happens between atom 1 and atom 2, when these guys are forming that bond, what happens is I actually get those orbitals overlapping to form this. So we've got our atom 1 and atom 2. And by basically crossing over their electrons so that those electrons are in the same orbital, that's how we end up with a covalent bond. Now, there are two different types of covalent bond, which we're going to move into now. Okay, so sigma bonds are the first type of bond we're going to look at. So sigma bonds, so that is the Greek lowercase letter. The reason I've used the symbol rather than just typing sigma is this symbol actually kind of helps us visualize what's going on. So if I've got an S, so this is an S orbital, and I've got a px orbital, and I cross them over. So what happens if I add an s orbital to a px and they're able to cross over end on end? This bond here is that, oh, that just looks like a circle. That is our sigma bond. The way I think of it is that if you sort of squint a bit and turn your head to the side, that sigma kind of looks like, and you might just have to trust me on this, like a Venn diagram. So that sigma works because it looks like the circle that's in the middle of a Venn diagram. When your orbitals overlap end on end, that's where we get those sigma bonds. So the other way to think of it, these sigma bonds form between an s orbital and a p orbital, or they form between two s orbitals. Oh, sorry, I should draw this. I drew this in the wrong place, didn't I? So if I've got that bit's decided not to delete. Never mind. So we've got our two s orbitals overlapping. That is a sigma bond in there. So if you think of sigma as being the Greek letter for s, which it kind of is, in order for a sigma bond to form, it either needs to be 2 S's or I need 1 S. Sigma bonds form by overlapping end to end. The next one we're going to look at works in a slightly different way. So pi bonds, so I'm hoping you've done enough like year 7 maths to know that that is pi. So we've talked about what happens with s orbitals. Pi bonds are what happens when p orbitals interact with each other. So if I've got these two p orbitals interacting with each other, they form this shape that, so if we've got like the plane of the atom, let me just, so this is where my 2 atoms are, and that is the plane, like the line of bonds between them. What happens is when these 2 things form a pi bond, my electrons are found above and below that plane. So I spoke about this in the SL, but when you look at benzene, it's got that delocalized ring of electrons above and below the plane. This is where that comes from these pi bonds. Now, sorry, excuse me. The reason I'm using the Greek symbol for this is because you start with 2 orbitals and then they form a line above and below, but that's how I remember it in the context of that Greek symbol pi. Sigma is the overlap that's in that Venn diagram. Pi is 2 things forming something on top and something below, which of course isn't in our pi symbol, but so pi bonds, just like sigma bonds you needed an s orbital, pi bonds are p orbitals only. So this has to be a py and a py, or a pz and a pz. So this is where you get that delocalized, well, not delocalized because we're talking about orbitals here, sorry. This is where you get that cloud of electrons either above or below, or both, the plane of those atoms. I am going to talk more about single, double and triple bonds later on, but hopefully you can see that if I've got a sigma, that is just my single bond. If I've got a sigma and a pi, that's a double. If I've got a sigma and 2 pi, that's where we get our triple bonds. So, for example, in ethane, ethene, ethine, I'm basically adding in pi bonds to get that double and triple bonding. We are going to talk more about that later though, so I don't want to go too far into it.
So formal charge is sort of a rule of thumb. It's not actually terribly accurate, but it's helpful for working out which possible, so if I've got 2 Lewis structures, which one's the best one, which one am I more likely to find, based on distributions of electrons around atoms. So there is a particular formula that you need to memorise. Unlike most of the formulae for IB, this one isn't given to you in the data book, so you do need to actually know this one. So formal charge, let me just get my pen, yes. So formal charge is equal to the number of valence electrons minus your number of non-bonding electrons minus half the number of bonding electrons. So valence non-bonding, which is our lone pairs, minus half of our bonding. So let's actually work through an example of this. So let's start by looking at sulfur dioxide. So sulfur dioxide, we can draw that in two ways. There are two different possible Lewis structures for sulfur dioxide. So we're just going to start with this guy here. So this version of it. Sorry. So let's look at oxygen number 1. So for oxygen number 1, the formal charge is how many valence electrons in an oxygen? 6, minus my non-bonding, which is 6, minus half of my bonding electrons, which is 1, which gives us a formal charge of -1. Then on my sulfur, my formal charge is, sulfur also has 6 valence electrons, minus, it has 2 non-bonding electrons, minus half of 6, which is 3. So 6 minus 2 minus 3 gives us +1. And then my second oxygen, the formal charge is going to be 6 minus 4 non-bonding electrons minus half of 4, which is 2, which gives us an overall charge of 0. So with formal charge, it's basically a way of saying, if this were an ionic compound, what charges would these things have? So this is one of the ways that I can arrange sulfur dioxide. Let's try a different way. So the other way that sulfur dioxide can form, because sulfur can expand its octet, what can happen is I can have sulfur double bonded to this oxygen and double bonded to that oxygen with a lone pair. My oxygens would each still have 2 lone pairs. So let's work through and see what our formal charges are. So I've got my first oxygen where the formal charge is 6 valence electrons minus 4 lone electrons minus half of 4. So half of 4 is 2, which gives us a formal charge of 0. Let's look at my sulfur. My formal charge is going to be 6 minus 2 lone electrons minus half of, it's half of 1, 2, 3, 4. But sorry, it's half of 8 because there are 8 bonding electrons. So half of 8 is 4, which gives us an overall formal charge of 0. Then for my second oxygen, my formal charge, it's got a valence of 6. It's then got 4 lone electrons minus half of 4, which is 2, which gives us an overall formal charge of 0. So that is why this expanded octet is preferred, because it leads to a 0 formal charge on all of the atoms in that compound. So let's look at 2 different Lewis structures for ozone and then talk about how resonance works. So I can have oxygen, lone pairs, bond, oxygen, lone pairs, double bond, oxygen 2 lone pairs, and it flicks back and forth with my double bond on the other side. Okay. So this is our resonance. Delocalization happens because when you actually identify these different bonds, so these guys that I'm now going over in black, these guys are our sigma bonds. So if I rotate that molecule so it's flat, so I've got oxygen, 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 and of course that middle oxygen is pushed back. It's got those sigma bonds joining them, but then I've got those p orbitals that are, sorry, it would be good if I could draw the nodes in the correct places. So if it's in what I'm going to call form 1, which is on the left, I've got a pi bond that forms here. If it's in what I'm calling form 2, my pi bond forms between those two. So if you work through the formal charge for each of the oxygens, one of these oxygens in the ozone molecule is always going to end up with a formal charge of +1, and one is always going to end up with a formal charge of -1. So neither form is preferred. So what happens is my sigma bonds get locked into that planar position. Then I've got my p orbitals crossing over and forming that delocalization. So in order for ozone, my O3, to form, I'll start at the beginning. How the ozone layer forms, I need to start with a standard oxygen molecule and split it apart into oxygen radicals. I keep drawing carbon for some reason. Then one of those gets added to another oxygen molecule, and I end up with the ozone molecule. Now, when I'm looking at breaking this bond here, I need to apply UV light, and it's fairly short wavelength. We're going to talk about bond enthalpies in a moment, but this is a double bond, or you sometimes hear it referred to as a bond order of 2. But so the reason the ozone layer is useful to us is because when that ozone is exposed to UV light, it forms an oxygen radical and oxygen. So when we talk about the resonance, what this basically ends up meaning is, yes, it uses UV light, which is why the ozone layer is important, but not as short length as the breaking of oxygen, because this is a 1.5 bond. It isn't as hard to break this bond as it is to break the bond of that oxygen to oxygen double. So this is how our ozone layer protects us from a range of different UV lights. So a shorter wavelength of UV light is used to break apart oxygen molecules, and then a longer wavelength of UV light is absorbed by ozone molecules and breaks apart that 1.5 bond. Now, you are too young to know about CFCs. They used to be used in like cans of deodorant, like spray deodorant. They also used to be used in refrigerators. Now, they're actually a really useful chemical. They're not flammable, they're not toxic, but the issue is, if, for example, when they get up into the atmosphere, my CFCs, so CCl2F2, CFC stands for chlorofluorocarbon. So when that gets up into the upper atmosphere, one of my chlorines can come off, and then that chlorine is super good at attacking ozone, to form oxygen, and also my ClO can then attack the oxygen radicals to form radical chlorine and oxygen, and then this radical chlorine feeds back in. So chlorofluorocarbons were phased out by was it a UN decision? Something like that, called the Montreal Protocol Accords, one of the two. And it's actually one of the few things that gives me hope that something may be able to be done about climate change. Because back in the 80s, we as in human race, were able to collaborate and actually get this done. So the ozone layer is still thinner over Australia and the southern parts of South America and Antarctica compared to a lot of other parts of the world, but it is remarkably better than like when I was a kid. So this second one, pay attention to it. It was asked on the exam last year, and I will need to double check the statistical, like the full examiner's protocol of it. I suspect it was not done well. So, if I take NO2, which is one of those pollutants that we get from car engines, I spoke about it when we did equilibria. So if I take NO2 and that gets up into the upper atmosphere, it can form nitrous oxide and oxygen radical. Then I take oxygen radical and I can react it with ozone to form two oxygens, and the nitrous can then react with ozone to form NO2 and O2, but then this NO2 can then come and do this again. So the issues that we have with the ozone layer is that a lot of these depletion systems are self-sustaining. So my NO2 or that chlorine radical, they're both generated by these series of chemical reactions. Okay, so this is another question on one of the reactions that leads into that bond enthalpy of light using UV energy. So we're going to start by looking at the enthalpy of this oxygen double bond oxygen, and that is 498 kilojoules per mole. You're then told in the formulae part of the data book that the relationship between energy, which is what this effectively is, and wavelength is H, oh, that looks like one of the Japanese characters, H nu. You know how I like talking about nu. Where this is Planck's constant, which is in the data book. So, I'm trying to work out the wavelength of light needed in order to break one molecule. So, what's my next step? I have nu, so that's a frequency. So the speed of light is wavelength, which is what I'm looking for, times nu, which means that nu is equal to speed on wavelength. So let's put this back into that previous one. So we've got E is equal to H C on lambda. So I'm trying to find my wavelength. So let's keep going. I'm not actually going to solve the maths. I'm just working through the algebra of how you would put numbers into your calculator. So this energy is in kilojoules per mole. Oh, sorry. Would be nice if I could consistently draw something that looked like a lambda. So I need to multiply both sides by Avogadro's number. So it's HC Avogadro's number on lambda. Then it's lambda that I'm trying to find, so I multiply both sides by lambda. So lambda E is Planck's, which is a constant, times the speed of light, which is a constant, times Avogadro's number, which is a constant. So my wavelength is Planck times speed of light times Avogadro's divided by that 498 that we got out of the data book all that time ago. Now, one important thing to note, this will give you a wavelength in meters. Most of the time when we're talking about light, we will convert that to nanometers. So nano is 10 to the neg 9. So you just need to do that quick conversion at the end. So in this section, we talked about covalent bonds being from overlap of orbitals. We talked about formal charge, and we talked about exceptions. I focused on expanded because we spoke about incomplete in the SL. We talked about delocalization and resonance. And we talked about how we know whether it's going to be sigma or pi. We looked at Lewis structures and formal charge. We talked about wavelengths of light for ozone and oxygen, and we talked about CFCs and NOxes. I might see if I can grab a question bank question for us to have a look at on VESPA and how that relates to expanded octet ones. I'm sorry, I forgot to do that in the PowerPoint. But let's continue on. Okay, so let's move on and talk about 14.2. So this is a comparatively short one, so we're just talking about hybrid orbitals. I'll explain what that is. and that is sp3, sp2 and sp, focusing on carbon and looking at Lewis structures, electron domains, geometries and the types of hybridizations. So let's talk about carbon. And let's talk about carbon in terms of orbitals. So we've got energy along here, and we've got the, sorry, let me move over slightly. So no, that isn't the 1s, that is the 2s and 2p orbitals. So we've got but when in the previous section I talked about bonds forming by overlapping orbitals. So in order for carbon to form bonds, what ends up happening is one of these s orbital electrons gets promoted. So we have three separate, so we have one electron in each of the p orbitals in order to get the orbitals to overlap to form bonds. So that's an important thing for us to keep in mind when we start looking at hybridization. So what happens is one of these s electrons effectively gets promoted into the third p orbital so that this s orbital can merge onto another one, as can these guys. sp3 are what we see in something like methane. So again, we've got our energy and we've got that promoted s electron into the p. Now, when you look at a molecule of methane, we've got a tetrahedral structure. I don't have one bond that is significantly different to the others. So if all of our electrons are acting in the same way, it means that I'm not so much looking at the difference between an s electron and a p electron. I have some sort of hybrid. So what we end up saying is that we have 4 sp3 because they're the orbitals that it was generated from. So this is for something like methane. It also works when you're looking at other single bonded structures like ammonia. We'll talk more about that in a bit. So this sp3 is what we call a hybrid orbital because it's a hybrid of the s's and the p's. So this forms 4 sigma bonds. All right. Okay, so sp2, as the name suggests, is what happens if I hybridize one s orbital with 2 p orbitals. So if these guys hybridize, I end up with an sp2. Now what that does is it leaves one p electron off on its own, so that makes it able to form a pi bond. So if it's sp2, I've taken one s and combined it with 2p, which leaves one of those p left over, which means that it's able to form those pi bonds, and that's what we see in ethene. We've got the sigma bond that are joining these guys in black here, and we've then got that leftover p electron, which leads to the formation of that pi bond, which is where we get the double bond in an ethene from. So if something is sp2 hybridized, it tends to have this trigonal planar structure, as the 3 bonds are evenly distributed around that central atom. Okay, so if we look at something that is sp hybridized, same story. We've got sp. So if something is sp hybridized, it is only hybridizing an S and a P, as the name suggests, which means that I've now got 2 electrons free to make pi bonds. What that means, this is how we get our triple bonded ethine. We've got that sigma bond that forms between, so these guys here form my sigma bonds. So one of these will bond to my second carbon and the other will bond to a hydrogen. And then I've got one electron free to form a pi bond along one axis, and a second orbital, I should say, free to form and make another bond along a different axis. So this is how we get, let me just change my pen colour, carbon to hydrogen, and you've then got this pi bond along one of our p orbitals and this pi bond from the other p orbital. So something that is sp hybridized, those have linear structures. So if something is sp3, it's tetrahedral. If something is sp2, it's trigonal planar. And then if something is sp hybridized, it's linear. That doesn't matter on whether it's a carbon or a nitrogen or an oxygen or whatever. If the electron arrangement, and that includes lone pairs, is sp3 hybridized, it's always going to be tetrahedral. If something's sp2, it's always going to be trigonal planar. And if something is sp, it's linear. Okay, so I largely talked about this on the previous slide. One thing I would like to point out is when we talk about hybridization, we're talking about the central atom. So if I know the hybridization of that central atom, I can work out the molecular shape. And if I know the molecular shape, I can work out the hybridization. So for example, we talked about sp3, sp2 and sp. So sp3s are tetrahedral. sp2s are trigonal planar. And SPs are linear. So it kind of works both ways. So if I know something has a linear structure, like carbon monoxide, I therefore know that that central atom is sp hybridized. If I know something is trigonal planar, like the carbonate ion, and I can't remember exactly how the bonding works on that, but it's flat. So again, I know that this central atom is sp2 hybridized. If something is tetrahedral, like I said ammonia earlier, so let's go with ammonia. I know that ammonia is tetrahedral, therefore I know that the nitrogen in that is sp3 hybridized. and vice versa. So if I work out that something is sp3 hybridized, by definition it has to have that tetrahedral shape. Let's talk about benzene, because you know it's not a chemistry class of mine if I don't talk about benzene. When we look at the shape of benzene, it's a hexagonal planar. But let's talk about it in terms of 4, 5, 6. Let's talk about it in terms of what's happening around each of my carbons. So we just spoke about this. What shape do I have around? Let's pick this carbon here. Around this carbon I am seeing a trigonal planar. Therefore I know that it's sp2. So if I rotate the plane of that benzene molecule, I will have my carbons bonded to each other. The hydrogens would be in that same plane, so I'm going to actually omit them for the moment. But then each of these guys has that pi bonding, which gives it that electron cloud above and below the plane. So it's like a carbon-hydrogen sandwich with like a cloud of electrons on either side. This is why when we talk about reactions of benzene, these things have to be electrophiles. They have to be attracted to basically get to those, to start working on those bonds. They have to be attracted to the electrons to deal with it. Okay. So hybrid orbitals we talked about. We talked about sp3, sp2 and sp in methane, ethene and ethine. We talked about electron structures, electron domains, molecular geometries and hybridizations. And we've only talked about sp3, sp2 and sp. Thank you so much. Have a fantastic rest of your day and I'll see you next time. Bye.